In the previous couple of videos, we discussed performing the unshift operation, which basically used for adding the node in front of the single linked list, right? That means that in front of the existing head node of the single linked list, we are trying to add a new value or new node with the help of a unshift operation. Now in this video, let's try to understand a function which basically removes the node in front of the single linked list. That operation is nothing but the shift operation. So as part of the shift operation, what exactly we will do is we will basically try to delete the very first node that we have on the singly linked list. That means that we will try to delete the node that is available at head of the singly linked list. Okay, so that is the purpose of the shift operation. Here we will not be taking any arguments from the user. In the end, we will simply return the node that we have removed. That means that whatever the previous head node that we had, right, that we will return as a output. Okay, that is the functionality definition. Now let's just see what all are the different cases that can occur when we try to implement the shift operation. Obviously, the first scenario that could come is basically the singly linked list is empty. That means that there are no nodes at all on the singly linked list on which we are trying to perform the shift operation. And we know how can we check if the singly linked list is empty or not, right? We have made a separate video for that. If you haven't checked it out, you can check that out. But anyway, we know how we can basically check if the singly linked list is empty. If it is empty, obviously, if the singly linked list is empty, how can we actually delete the very first node, right? And head and tail will be at null or none based on our programming language that we are using for implementation, and length will be at 0. So obviously in this case we will not be able to perform shift operation or the removing the first node in the singly linked list. So we will simply return null or none. Okay, so that is the first scenario. And the second scenario is basically where we have only one node inside the singly linked list. If we have only one node in the singly linked list, right, we will have both head and tail node at the same node. That's why we have to make sure that whatever the only node that we are having, that itself we are deleting. That means that singly linked list is becoming empty. So to represent an empty singly linked list, what we will do, we will assign head and tail both with null or none. That's why here if we have only one node, update head and tail both with null or none, and none is for the people whoever is using Python for implementation. Okay, so that is something that we have to remember. Along with assigning, what we have to do, we have to make sure that length also we are updating it with 0, because whatever the only node that we have, we are deleting that. As a result, single linked list becoming empty, which is nothing but 0. The length has become 0. Here, before assigning null, you can actually read the head node, because in the end we have to return the node that we are deleting, right? So just for returning that node, before assigning head and tail and length with the appropriate values, make sure that you are reading the head value so that in the end you can return that value, return the value of head, or you can return the node itself. Okay, that is based on your choice. Okay, this is the first scenario where we have only one node, and the third scenario is obviously greater than one node inside the singly linked list. In that case, what exactly we will do is we are trying to delete the very first node inside the singly linked list, right? So we basically have the impact on the head reference that we are maintaining inside the singly linked list, because whatever the node that is at the head, that itself we have to delete. To delete that, what we will do is whatever the next node that is there after the current head node, that node we will update it to the head of the singly linked list. In this way, we are basically losing the track of the previous head that we are having on a singly linked list. So simple operation, simple assignment operation. Here we have to delete the node that is at the head. That's why we will make sure that whatever the next node that is there from the current head, we will simply update that to head of the singly linked list. because we are maintaining head and tail of the singly linked list, our head will be pointing to the node that is at the second position basically. In that way, from head to tail, we still have the singly linked list, and whatever the node that was there previously as a head, that will get deleted. Okay, so that is the algorithm for removing the or performing the shift operation when we have more than one node. What we will do, we will simply update the head to the next of the head node dot next. Okay, that is something that you can simply do using a simple assignment operation. Along with that, we have to make sure that since we are deleting one node from the singly linked list, we have to make sure that we are decrementing the length by 1. So length will be length minus 1. Okay, so those are the scenarios that could come when we try to remove the very first node of a singly linked list. Okay, now let's just try to write the pseudocode for shift operation. Okay, so as part of the shift operation, our aim is to delete the very first node that we have on the singly linked list. Obviously here, what we will do, we will write a function called shift, and this function will not take any argument because it knows that it has to delete the very first node in the singly linked list. That's why we will not take any argument. So as part of the first check, what we have to do, we have to check if the singly linked list is empty. If at all, if the singly linked list is empty, we will simply return null or none based on the programming language that we are using for implementing. Okay, that is the first scenario. And the second scenario is basically we have only one node. That means we know the length of the singly linked list, right? Whatever the length that we are maintaining, if it is equal to 1, that means that singly linked list has only one node in it. Otherwise, the other comparison that you can do is basically if you have only one node, we will make sure that both head and tail are pointing to the same node, right? So the other comparison that you can do is head is equal to tail also you can do, because both will be at the same point, at the same node. As a result, they will match. But I tend to use the length based comparison for checking if the singly linked list has only one value or not. If at all, if we have only one value, what we will do, whatever the head node that we have, we will update it to null/none, and similarly we will also update tail node to null or none. Here one thing that you have to remember is none is for the people who are using Python for implementation. Okay, so that is something that you just have to remember. Anywhere I am using null or none, it is for the specific people whoever is using the respective programming language like I mentioned previously. Okay, after updating head and tail, we will update length to 0, because whatever the only node that was there on the singly linked list, we have deleted that. As a result, the singly linked list has become empty. As a result, the length will be 0. So this is the case where we have only one node in the singly linked list. Now let's just try to handle the otherwise case where we have more than one node in the singly linked list. In that case, like I mentioned previously, what we will do, we will simply update the head with the whatever the next node we have from the existing head of the singly linked list. This is the head node and this is the tail node. Let's assume that we have 3 nodes on a singly linked list and we have to delete the very first node. So we will, if we want to delete, we will simply move the head to the next node. In that way, we will lose this, the head that we had previously. That's why we will simply update head with the head node dot next. Okay, and we have to make sure that we are decrementing the length also by 1. Okay, so that is something that you have to remember here. And couple of people, what exactly they will do is, here we already had the next node on the previous head, right? To make that also null, first what exactly they will do is they will read the current head is nothing but the head, right? Now On this, after updating the head node, what exactly they will do is they will also set current head dot next to null or none. Okay, so this is some optional operation, you don't have to do it, but just some people are very particular about updating the next to null or none based on our the way we are implementing. They will make sure they try to update the next of the whatever the head node that we had previously, because in the end we have to return the node that we are deleting, right? That is nothing but the current head. If we simply return the complete head, the complete node, using the next, user still has a possibility to traverse the remaining singly linked list. So they just don't want to give that functionality. As a result, before returning that value, they will make sure that they assign next to be the null or none. In the end, we will simply return whatever the current head that we have inside the current head variable, which will basically have whatever the value we had at the head node in the singly linked list. Now let's implement the shift operation in our singly linked list according to the steps that we have discussed previously, right? So in the end, as part of the shift operation, what we will do, we will basically delete the very first node, that is nothing but head node. We will try to delete. As we are trying to delete that head node, whatever the next node that we have after the head node, that will become the very first node in the modified singly linked list. As a result, we need to make that node as a new head of the singly linked list. But anyway, after deleting that node, we need to return that node back to user. That's the reason why the return type of the function will be node, and let's just name the function as shift, and it will not take any arguments. Just like how we had three scenarios in the case of pop operation, basically the three scenarios are when we are trying to perform the shift operation on an empty singly linked list, and the second case is when we have only one value, and the third case is where we have more than one value. So these three scenarios, similarly how we have handled in the pop case, we have to handle in the shift operation as well. But it is just that we are trying to do the same thing on the head side of the singly linked list. So first here, let me just read the head node of the singly linked list so that we can return that after deleting in the end. So here what we can do is, let me just read the head, and after that let's try to write the logic one by one, logic for honoring each and every case that we have discussed. So let's just try to honor the case where the singly linked list is empty. If the singly linked list is empty, obviously there are no nodes at all, so we can't delete anything. As a result, we can return null itself, or else we can return the new node itself, because anyway, sorry, head node itself, because the head node will anyway be null. So it is completely up to you whatever you want to return. Otherwise, if the singly linked list has only one value, let's try to write the logic for that one. If the singly linked list has only one value, length will be equal to 1, or you can do this dot head is equal to this dot tail. That is also absolutely fine. Now when we have only one value, both head and tail are pointing to the same node, right? And that only one node, right now whatever is the head, that is also the tail that we are trying to delete. As a result, the singly linked list will become empty. So to represent that state, what we will do, we will update the head to null, and we will update the tail to null, and we will decrement the length by 1, or else you can directly make the length to 0, because anyway when we have only one value, even if we decrement it, it will become 0. In the end, what we need to do, we need to return the head node here. So return head node that we have deleted. Okay, so second case also successfully handled, and the third scenario is obviously when we have more than one value in the singly linked list. So this is one of the easiest cases that we can handle here as well. Anyway, we have the access to the head node, and all we have to do is we have to update the next of the current head node to the new head of the singly linked list, so that it will become the head of the singly linked list. Anyway, we will process the nodes only from head node to tail node, right? So we would have deleted the current head of the singly linked list. So what we can do is this dot head So what we can do is we can simply update this dot head is equal to whatever the head node that we have read, right? So dot next. So that will be the new head of the singly linked list. As we are deleting one value, what we can do is we can decrement the length by 1. So this dot length equal to this dot length minus 1. Okay, in the end we need to return the head node that we have deleted. Okay, so this is the only change that we need to remember. Anyway, in the singly linked list that we are implementing, from head node to tail node only we will do the reading or whatever it is, right? So by simply updating the head node to the next of the current head node, it basically looks like we have deleted the current head of the singly linked list. Okay, so that is something that you need to notice here. Okay, now anyway, the logic has been handled successfully. Now let's just try to validate the same thing on a group of values we have on the singly linked list. So here in the beginning, let's just assume that there are no values at all on the singly linked list, and let me just comment out this unshift also, and let me just perform the shift operation on the singly linked list. Anyway, since there are no values at all on the singly linked list, it is empty, right? As a result, the logic will go on to this, and obviously, since it is, no value is there, the traverse function also does not print anything. So the first traverse and second traverse both should basically print the empty lines. So if we see here, okay, again I made the same mistake of not using the arrow. Where exactly is that? Here. Okay, here also I need to use the arrow. Okay, if I execute this now, see, both lines are empty because there are no values at all on the singly linked list. Now to test the second scenario, let's just have only one value on the singly linked list. Now as part of this traverse, this 0 should be printed. As part of this shift, whatever the only one value, which is nothing but head and tail, that is the only node, and that itself is the head and that itself is the tail, and we are deleting that. As a result, the singly linked list will become empty and the traverse should basically print nothing. So as part of the first traverse we should see 0 and second traverse should be empty line. So that is what we are seeing on the console as well. Now let's just try to test the scenario where we have more than one value, and if we perform the shift, this first value 0 will be deleted and this 10 will be the modified head and tail of the singly linked list, and that's what we should see as part of the second traverse of the singly linked list. So see, as part of the first traverse 0 and 10 are the values, and as part of the second traverse, as we have deleted 0, we have got only 10. Similarly, you can add as many values as you want onto the singly linked list, and the remaining values whatever we have after deleting the existing head node, we will print all those values. If at all, if we perform the shift once again, after performing the first shift we've deleted 0. After performing the second shift, the modified singly linked list head is 10, right? That also we will delete as part of the second function call. As a result, the resulting singly linked list has only minus 10. That's what we should print. So you can add as many values as you want according to the steps that we have discussed. You should see output in the console like you see on the screen. Okay, so that is the implementation of shift operation, in which we will basically delete the head node of the singly linked list, covering all the scenarios. So now we have successfully completed all the functionalities which basically add and remove at the end of the singly linked list and at the beginning of the singly linked list as well. Going forward, we will try to implement basically getting, updating, inserting and remove related operations. Okay, now that we have implemented the shift operation on a singly linked list, let's just try to analyze the time complexity and space complexity of the same. So you might be wondering what is the best case and what is the worst case of implementing the shift operation, right? When we try to perform the shift operation on a singly linked list, there will not be any best case or worst case, because we are trying to delete the very first node on the singly linked list itself, because even if the singly linked list has n number of nodes, even if the singly linked list has only one node, the operation is very similar. When we had only one node, we will simply update the head and tail and length with appropriate values. Even if we have more than one node, or even if we have n nodes, we will simply update the head node to the next of the current head that we are having. So obviously, be it the singly linked list where we have only one node, or be it the singly linked list where we have n number of nodes, we will simply delete the very first node by using the simple update operations. As a result, the time complexity will be order of 1 only. Okay, so now let's talk about the space complexity involved in performing the shift operation. So if you remember, we have basically defined a variable called current head, right? Where we tried reading the head node. Besides this read operation, and we after this read operation, we have basically updated the head node with the head node dot next that we already had inside the singly linked list. The only memory that we are consuming is for this variable where we are trying to read the head node, so that in the end that node is getting deleted, right? Basically we have to return in the end. So obviously that variable will take only constant amount of memory. And even if you take the scenario where we have only one node also, we are updating the head, tail and length that we are maintaining. We are updating it with the appropriate values with null or none and 0. So those update operations will take only constant amount of memory for implementation, right? So even if the singly linked list has only one node, even if the singly linked list has n number of nodes, whatever the shift operation that we are trying to perform will take only constant amount of space for implementation. Okay, that's all there is in terms of time and space complexity analysis of a shift operation on a singly linked list. Okay, so thanks for watching. I'll see you in the next functionality implementation.